Integrated simulation. I'm going to talk about two simple concepts. The first one, buildings designed with an awareness of climate should look different on each facade. And this was a quote from our visiting professor, Clark Brockman, in 2013. And he was saying that buildings should not really be like the Arts Tower. The Arts Tower, where are we? North, south, east, west facade, all the same. But of course the sun, the wind, is not the same in each direction. Our use of this building is not the same on each direction. This is a seminar room, that's a kind of studio, that's a toilet. They're all different functions, but in this building they all have the same facade. And I take that step further and say buildings designed with an awareness of climate should look different all over. Not just on the different faces, but the different faces should also respond to their local climate. And this is an example project which has actually been built now in Leeds by Field and Clegg Bradley architects. And this model is really interesting. This is a solar radiation simulation which they have then printed onto paper and stuck onto a cardboard model. And what they're looking at here is that the amount of energy and the amount of light that building receives varies across all of its windows because of orientation, because of overshadowing from other buildings. And so what they're doing here is not just saying that east, west, north, south should have different configurations, but that within the same facade, that configuration should respond to the local climate. And in this module, we give you the skills that allow you to design in this manner. Okay, where do we begin? And this kind of image I use to kind of indicate when you start looking at simulation and when you start you open a piece of software, it can be very overwhelming, and there are 4,000 different buttons you can press. Now, the key thing is, for simulation, you don't need to use all of the buttons. And the software that we're going to use in this module has many, many capabilities and many, many buttons, but we don't need to use them all. Okay? And you can still get very effective simulation by learning and mastering a small set of buttons. Now, I don't know much about flying planes, but I imagine that most of these controls and buttons get left alone for most of the flight. I don't imagine the pilot is sat there constantly changing all of these. Some of these are probably about sort of cabin temperature and lots and lots of things. And it's kind of similar with simulation. You don't need to use all the tools. You can go in, use the tools that are useful to you, and then come out again. Okay. Simulation workflow concepts. Now, by workflow, I mean your kind of method. How are you using simulation as part of a design process, or if you're in practice, how are you using simulation as a consultant to advise other designers to work in a design team? And I'm going to talk about three concepts: linear, multiple, and iterative and integrated. So linear would suggest that in a workflow, you start at the beginning, you work through, so analysis, concept, proposal, product. And in a linear workflow, at different stages, you would be using different types of simulation. And this was an Autodesk slide from 2013. And sorry, let's go back to that one. And what Autodesk was suggesting is that at different stages in the design, you use lots of different types of software for different simulations. Now, this is not the workflow that I'm proposing in this module. Okay, next one, multiple workflow, which I also call import-export. And again, this is not the workflow that I'm proposing in the module. In a multiple workflow, an import-export workflow, what you have is a whole family of different softwares. It's probably a bit small for you to read, but here we've got Vasari, Ecotect, ID Build, Revit, Rhino, SketchUp, B10, Ecotect, 3D Studio Max, Design Builder. What else have we got? That's probably IES. Lots and lots of different softwares. And what these little green arrows are indicating is the process that you get information from one software to another. And it's an import-export. So, for example, here you would have to export a DXF file. Then you'd have to import that DXF file. Then you'd probably have to fix it. Here you've got GBMXL export into Ecotect Analysis. So the software are linked, but they're not integrated. So yes, each green arrow is an import-export function. Very complicated, I would say. The workflow that I'm proposing is iterative and integrated. And I'm going to look now, this is my, my diagram of an example of an integrated workflow. Some of the software that I'll mention here we are not using anymore, and that's the nature of software. The software that we were using on this module 3 years ago, most of that has now changed. Some of the software we were using last year no longer exists. So we have to keep adapting, and that's the nature of software. Whatever software you're using today, I can guarantee you will not look anything like that in 5 years' time. Okay? But you have to engage. So in a design process, or as a consultant working with a team, quite often you might start with hand drawing. It's not uncommon for engineers and architects to sit down and draw, to start a thought process. And then, fairly quickly, those hand-drawn sketches are interpreted into a piece of software. And in this program, in this module, sorry, the software we're using is Revit. Okay? Could I just have a show of hands? Who has used Revit before? 1, 2. Okay? That's fine. 3. So I'm not expecting you to have used Revit before. The 3 who have used it, would you class yourselves as experts, intermediate, or beginners? Experts? Intermediate? Beginners? Beginners. Okay. Well, that's good. That's good. So we're going to introduce you to Revit. I'll explain in this presentation why we're using Revit, but I think the important thing to know about Revit is it is the kind of industry leader. It is the most commonly used BIM package, so BIM, building information modeling, i.e. you're building a three-dimensional model. But also we use Revit because it offers the best integrated approach. And you'll see that in today's presentation, and you'll see that in the module. So we feel it is the best software to be teaching you at this moment. We will bring in a few other pieces of software as well. Okay, so we've got Revit, and we've brought our sketch information into Revit. And immediately, the yellow boxes are outputs. we immediately have some potential outputs. We can use a computer-controlled router, we can use a laser cutter, we can use a 3D printer, we can use a 3D MakerBot, a polymer printer. So this is equipment that we have this equipment in the school. So immediately you can link that computer model with a 3D output. So there's something very interesting there about being able to go from a sketch into a computer model into a physical model. I'll show you some examples. Okay, just zoom out a bit there. And we also have another series of outputs from Revit. We've got conventional 2D drawings, just plans, sections, elevations, daylight analysis, conceptual energy analysis, building energy analysis, 3D images, solar and shadow analysis, and in a practice environment you've got quantities, schedules. You can count how many windows you've got. You can cost the building in Revit. So these are the kind of outputs that we can do immediately. Okay, just zoom out a bit. Last year we were also using Vasari. Vasari is was kind of like Revit Lite. It was this kind of easy form of Revit. So we were using that. It was quite a good piece of software. Autodesk have killed it. Okay, it's gone. And that's the nature of what Autodesk do. They introduce software, we trial it for them. Sometimes they kill it, sometimes they progress it. What they normally do, and they are doing it with Vasari, which is good for us, they're taking elements and they're integrating it into Revit. So the scope that Revit can offer is growing year by year. And also it's fantastic because as more and more is incorporated into Revit, that means you have to learn fewer software packages. So this year, for example, you don't need to learn Vasari, whereas last year we had to use Vasari for some of the features. Okay, 3D Studio Max Design. Again, previous years we were using 3D Studio Max for daylight visualization and lighting visualization. Again, it's a different package. We don't need to do that anymore because the tools that we need are now integrated into Revit. Now, the thing that is important in this workflow to note is that although we were using these three pieces of software, they were linked live. So this thick black line was showing a live link. So in other words, you could make your model in Revit, but you could open it in 3D Max. You could open it in Vasari. You were not importing, exporting. It was linked live. Now, this year, we don't need to bother with Vasari, and we don't need to bother with 3D Studio Max. We can concentrate on Revit, which makes everything a lot easier. Okay. The important thing to note here was that in an integrated workflow, if you make a change in the Revit model, it will automatically be transferred into the integrated software. And then that will again be transferred into the analysis and the output because it's linked. The workflow becomes iterative and recursive, meaning you can make a change, you can simulate, you can assess that, you can then go back, make another change, simulate. And this is the process. It's not linear, it's iterative, whereby you're making design changes, you're simulating, you're implementing the analysis, making changes, simulating. Much better workflow. Okay, I'm going to now, in the last 20 minutes, show you some example simulation workflow. And the examples I'm showing you are from the studio which I run, which is called Interactive Urban Skins. And I think you'll find it hopefully interesting because it's work done by students who have taken this module but then taken that further into their own design work. So, critical analysis of local climate data as a start point. So we start with local climate data. You can't design if you don't understand your local climate. Okay, so here we were working in Switzerland and working in Sheffield, looking at the different climates. And we were working with simulating future climate change. Now, we're not teaching this in this module. This is a much more complex piece of software. But this was a piece of software called MVMet, which allows you to simulate urban conditions in the future. So you no longer have to work with the climate data from today. As you can see, it's not a very kind of graphic piece of software. It's quite a basic piece of software. If you are interested, Dr. Chengzi Peng in the School of Architecture is pioneering this in his research. It takes about a week to calculate. So you plug the data in and you need a computer to just sit and calculate for a week. I'm not teaching you that. I'm just showing you it. Okay, solar radiation. We are covering this. So being able to understand and simulate the energy from the sun on your site. Energy is related to light as well. So the more energy you have from the sun, the more light you have from the sun. So absolutely critical that you can simulate the energy from the sun on your new building, on existing buildings, assess the impact of your new building on its surroundings and vice versa. So we will be covering this in the module. Shadow path and solar access. Again, really important that you can simply simulate the shadows cast on your site. In the UK, we do get sunshine. You might not believe me, but it's not always like this. Okay? It's quite often like this. But when the sun comes out, we need to be able to simulate the shadows cast by that sun. And also be able to simulate the direct sunshine that we might be able to admit into our buildings. So these are some examples of a student in Lucerne, in Switzerland here, modelling the shadow path around their site. And very easy to simulate that at different times of the year. And here we have it, the shadow path with the dotted red line overlaid with a wind flow simulation. So being able to simulate the path of the wind, the velocities of the wind in an urban situation. Okay, urban wind flow. We will cover this in the course. Previously this was covered in Vasari. It's no longer available Vasari is no longer available. We'll be covering it in a piece of software called Flow Design. But we'll come to that in a later session. But again, being very simple to be able to look at the wind on your site, look at the wind coming from different directions, different velocities, look for the impact of your proposed building, or look at the existing wind conditions on that site. Okay, just some examples there. As you can see, looking at plan views, looking at three-dimensional views, looking at sectional views to get an idea of how that wind is working on the site. I mean, wind design, I would say, for architects and for normal kind of engineers, it's not something you would specialise in, because there are aerodynamicists out there who are real specialists in this field, and they have much more complicated software. But it's good for us to be able to have an awareness and an understanding of wind flow. Okay, solar radiation, as I mentioned before. In this example, this is a very detailed analysis of the energy from the sun impacting on this building. And we've got some different comparisons here. If you look on the bottom, we have the building with a slightly different shading configuration. And if you look at the top view, there's a deeper shading system, and you can see the kind of the impact of that here in terms of that reduction of energy on that facade below the shading. Also able to simulate the fact that because of building's height and because of overshadowing, the energy incident on a building facade might vary over that facade, as I was mentioning earlier. So if you kind of look here, it's probably a bit small, but you can see that in the bottom left-hand corner here, we've got a sort of dark blue, which on the scale indicates a lower energy level. And then on the same facade, in the top right-hand corner, we've got yellow, which is a much higher energy level from the sun. So really critical as a designer to be able to use that. That's just a close-up of that. Also being able to be quite specific about the period you want to analyse. So this one, for example, is from the 21st of March through to the 21st of September. So this is a summer analysis. And then the student also looked at winter and looked at the implications of that. Building energy performance analysis. So we start fairly early in the module with what we call conceptual energy analysis. So what we mean by that is being able to test the energy performance of a building without having a detailed design. So in the examples here, you can see we've just got three quite simple building shapes. And the difference being that this version on the left has smaller windows than the middle version, and then the version on the right has some shading on those windows. In this example, the building shape is the same in each case, but other students worked with different building shapes. And the ability to, very early on, test the energy performance. So before you've spent weeks and weeks designing a building, do some initial studies and look at which option is performing best. And the whole importance about integrated simulation is that you can use this quickly in the design process. If you go back in time, let's say 5 years, you couldn't do this. And you would have had to take this into a different package, run the simulation. In a practice environment, you would have often got your energy team or your engineering team to do it, and it would have taken weeks. But now you can do this in a matter of sort of hours. So we'll cover that in the course. And these are the kind of outputs you get, where you can break down the energy performance of that building, heating, cooling, lighting, looking at potential renewable energy usage. Okay, really important one. Daylight analysis, solar tracking, and glare analysis. Now I think certainly for kind of architects, architectural designers or engineers who are working in a team with architects, lighting and daylighting is really important. I think it's for architects, it's the one that we can lead on, because the software that we'll show you for daylighting analysis is really sophisticated. Some of the other software we use has lesser degrees of sophistication, but the daylighting is very accurate, very sophisticated. So the example here, there's a series of images here where the student is simulating the effect of a shading device. So there's a shading device through that window. And as we go through the slides, he's changing that shading device and looking at the effect of daylight on that space. Now, in this image, it's a kind of visualization, so it's giving you a good feel for the quality of daylight and what the view is like out the window. But we also need to quantify that and put metrics to that. So at the same time, we have an illuminance study and a daylight factor study. We'll cover this in the course, don't worry about understanding that now. But being able to put very accurate quantities to that daylight. And this is the same space with the different shading configurations. That was on the level of a room, but also we might want to be able to do that for a whole building. So these are the plans, floor-by-floor plans of a building, looking at the illuminance in that building. I think this is throughout the year. Okay. Internal airflow. Now, again, this is not, it's not something that we cover really in this module. It's too complex. We haven't got time to cover it. But I'll introduce you to the software. This was a student from 2 years ago who decided that he would invest a little bit of time himself to learn this piece of software. And this is simulation CFD, computational fluid dynamics, and it enables you to then look at a very detailed airflow simulation within a room. It's not covered in this module simply because the module would get overloaded, and we have to try and keep a module sort of within the limits of what you can achieve. Notionally, a 15-credit module is about 150 hours work, and so we can't cover everything. Okay, then applying these skills in the design of buildings. So in this example, the student took the simulation skills that they learnt in this module. They then took the some of the skills they learnt in a different module, which was the BIM module, and they brought those skills together to apply that on their project design. And what they're doing here is they're taking the radiation values on the building, exporting that, and then bringing that into Dynamo in Revit to use that to control a shading device. So this shading device here is optimized by the radiation incident on that building. So you have a really kind of sophisticated optimization of that building facade. And that's the kind of view of the building. And I think I overlay in a moment. Yeah, look at the shading, the degree of kind of closed shading, open shading. And then we overlay the solar radiation onto it. I'll just go back. And you can see that shading, it's not a kind of approximate north facade has more, less shading, south facade has more shading. It's a really kind of optimized relationship with the solar performance. This is a different project. This was the one that I showed you the radiation studies for earlier. And I think this image is interesting because, I mean, for me, I think this is a really fantastic image, really kind of evocative image. This image was produced in Revit, and the simulation skills that we deliver in this module, this student then used in his design project. So the rendering was done in Revit. He's then, in Photoshop, he's added the rain and the people. But, it's basically a Revit simulation. And same as this. And this student, before this module, had no skill in rendering in software, none whatsoever. So for this student, it was fantastic to develop these visualization skills. And these are some of the other images. Okay. When we get into the session on daylighting and rendering, what is fantastic is, and I cover this a little bit in the next session as well, Autodesk, they give away all of their software to students, and they have a cloud rendering service. They give that away to you free as well. So all of these renders that we're looking at here were not done on the student's computer. They were done on Autodesk's servers. And I'll show you how to do this. But it's also fantastic for this idea of iterative workflow, because if you imagine you're rendering on your computer one at a time, and it takes 7 hours. So you send a rendering, right? Okay, what am I going to do? I can't work on my computer. Okay, and then that rendering comes back 7 hours later, and you think, a few problems there. Or let's say you're working in a design team, and your client says, I'd like to move that window from here to here. And you say, oh, well, it took 7 hours to render that. I'm not moving the window. I mean, you can't do that. The fantastic thing with the cloud rendering that I'll show you, you can send 20 renderings off they go, onto the Autodesk servers. Now, depending on how busy the Autodesk servers are, they might come back in 10 minutes. They might take a few hours, but the important thing is they're not on your machine, and the number of renderings you send will not slow down their servers, because the whole world is sending renders. They must have a big server farm, and it means that you can use this iteratively. You can do lots of renders, bring that to a tutorial or in a practice environment, bring that to your client, bring that to your engineers, look at an energy performance simulation, make changes, send those renders again really quick. So it's the whole idea about this iterative workflow. You can change, you can make modifications, you can re-render, re-simulate. And this is a different project. Again, linking the solar radiation in Dynamo to control a shading device. And this is one of the internal visualizations. So this shading screen is controlled both by the radiation levels that are simulated, but the idea was also that there could be radiation sensors on the building that would control it. And again, this is all Revit, all done in Revit. Looking at the daylight factor in that space, simulating that with the panels 40% shut, 100% shut. And again, because the whole basis of the simulation is that you need a three-dimensional model, the student uses that to its maximum benefit here. This is the model in Revit. It's not just a model which is produced for simulation, but the student's using it for visualization, it's used in the report, it's used in reviews, it's used to communicate the design. And by investing the time early on to make that really good model, that then helps with the design for the rest of the year. So again, these are all Revit renderings. Very effective nighttime renderings. I'll just go back. What you will find when we come to renderings, I'm not teaching you 3D Studio Max, so I'm not teaching you kind of real high-end photorealistic rendering, but as long as you're kind of controlled, so if you look here, this rendering, all the buildings are white, and all the surfaces are white, and the building has a little bit of colour, and it's effective. What you'll find with renderings, as soon as you start putting materials on badly, it will spoil the results. But equally, nighttime renderings, very effective. A lot more forgiving in terms of the quality of the model. And this idea about workflow research was very important, that I encourage the students, and I encourage you in this module, not just to learn the software and use the skills, but to try and think about the process. Think about how you would use that in a practice environment, how you might use that in your own design work. So this was just an image by the student trying to kind of map a software path through their project, and kind of being critical about it. So, for example, here, flow design, he's commenting that it was difficult to use, didn't work very well. There's other comments about, where there was perhaps a lot of Photoshop editing. And as soon as you start editing something in Photoshop, it's no longer linked to the model, and it's kind of not iterative. So having that critical awareness of your workflow. Okay, almost finished. So we've come a long way. AutoCAD started in 1982. We developed here, University of Sheffield, we actually developed the first 3D BIM software in 1985. Unfortunately, we were overtaken by Revit, and they are now the market leader. Revit started in 2000. Revit daylight analysis was only implemented in Revit 2 years ago. Before that, you couldn't do it. So we've come a long way, but my argument is that we need to go much further. And for us to be able to design really integrated, energy-efficient buildings, we need to be more sophisticated. Okay, thank you.